highlighted. Doesn't want to go away. Don't worry about it. If you look at this ring, rotate it the right way. Let's look at it like this. Okay, so you've got 6 blue chlorines and 6 white hydrogens. The blue chlorines are occupying positions on this ring. Now the ring's not flat, but if you imagine that it's basically flat with a little ripple in it, so take the lawn chair and lay it flat pretty much. Those 6 chlorines are in what we call an axial position. They point perfectly perpendicular to the plane of the ring, either straight up or straight down. There's one on each carbon. Up, down, up, down, up, down. They alternate around the ring. So if you take one and it's pointing up, the 2 neighboring axial positions point down. The hydrogens, the white spheres, are all along the equator of the ring, and they're called equatorial hydrogens. The point of this, and it is a significant point, is that the equatorial positions are less crowded than the axial positions. The axial positions are more crowded than the equatorial. Let me put this into the space filling mode, and you can see that better. The space filling mode is the closest to the true radii of the atoms and how closely they're bonded together. You can see that these axial positions, particularly what I call the 1,3 position. So this position is axial. If you say it's on carbon 1, the next axial on the same side is on carbon 3. That's called a 1,3 diaxial interaction. In these CPK, or space filling pictures, it's very, very bad for 2 of these van der Waals spheres to touch. Potential energy explodes when that happens. And these do touch. If I rotate this down, you can see that. See all this crowding right here. That doesn't happen in the equatorial positions because of their location. Okay, so if you have big groups on a cyclohexane ring, they are more stable being being equatorial than they are being axial. Another way of saying that is that bulky groups prefer to be equatorial on a cyclohexane ring. And the bigger they are, the stronger they dominate that preference. Now, why is this significant? It's significant because this ring is not as you see it. It's constantly flopping around. Now, it exists almost always in this chair form, but what amounts to the carbons in the seat of the chair, the back of the chair, and the foot of the chair keeps shifting. So one moment a carbon may be in the seat of the chair, the next moment it might be the back of the chair, because the ring is flopping like a big bird. All the carbons are flopping up and down, and what that does is every time there's a total flop from one chair form to another, everything that's axial becomes equatorial, and everything that's equatorial becomes axial. There's a total switch going on all the time. And it's trying to happen thousands of times per second. So imagine you're a big, bulky group on a cyclohexane ring. You're trying to stay equatorial to give you more room for your electron cloud, but the flopping of the ring keeps trying to push you into an axial position. You're going to resist that. If you're a methyl group, you can resist it somewhat, but you're still going to end up being axial some of the time. If you're a 4-carbon group, then you've got more power and you're going to stay equatorial all of the time and prevent the ring from flipping it completely. So the motion of the ring is controlled by the size of the groups. The ideal is to get as much size as possible equatorial and as little big size as possible axial. Now the way this plays out, for instance, in glucose, is that glucose is a ring that has 5 big groups and 5 small groups on the ring. One of the 6 carbons is actually an oxygen, so there are some substituents missing. But the 5 bulky groups prefer to be equatorial. And so glucose, because of what we call its stereochemistry, is the only compound that can have all 5 big groups equatorial simultaneously. Okay, because imagine you have one bulky group equatorial and one bulky group axial. If the ring flips, it's a wash. So one bulky group gets thrown equatorial, which is good, but the other group gets thrown axial. Nobody escapes the flip. What was axial becomes equatorial, what was equatorial becomes axial, and there's no opting out. Once that ring flips, everybody has to switch. So it's complicated. The best scenario is where all of your big groups are equatorial and they just lock the ring in that position. It doesn't flip at all. And glucose is the only one of the so-called aldohexoses that has the right stereochemistry for that to happen. Mannose, for instance, can get 4 of the 5 equatorial, but always has 1 axial. And that caused mannose to lose, evolutionary-wise, as the main energy source of the most common aldohexose. So stereochemistry and these little tidbits of information really do matter. If you want to understand carbohydrate chemistry, this has to be a piece of information that you can use when you see it. Okay, now the book probably, I'm sure it does, I looked at it, has a number of problems where you calculate differences in energy between different equatorial, axial, substituted cyclohexanes. Don't worry about that. That can be done by computer. All you have to do is understand the concept, which is that bulky groups prefer to be equatorial, and for an obvious reason, they're less crowded there, and so the numbers go up as crowding increases, and they go down as crowding decreases. Otherwise, it can be quite complicated to figure out one of those problems in your head. If you make models, it's very easy, but it can take you 15 minutes to make a set of models, so they're not easy problems to do. Let's see. That's the chair form, and it's in equilibrium with other flipped chair form, but actually there's also another form. That your book will talk about. It's also reasonably stable. So if I have a chair form and I pick up the carbon that is the foot of the chair, and put it on, rotate it onto the same side as the carbon that's the back of the chair, then you get a sort of quasi-stable structure that's called a boat form. The boat form is not as stable as the chair form, but it's not bad. And then, of course, that boat form can either go back to the original chair form or form a different chair form where different carbons of the seat of the chair and the back of the chair and the foot of the chair, etc. So this goes on thousands of times per second. The difference in energy between the chair and the boat form is about 8 kilocalories per mole. What does that mean? Well, at room temperature, it means if you had 100 cyclohexane molecules, this plain cyclohexane, and they're flipping all around, and you freeze them, 99 of the rings would be in a chair form, and 1 would be in a boat form. So that 8 kilocalories translates into only a 1% share in the structure of cyclohexane. Little energy can make a big difference. Since it's rarely in the boat form, all you have to do when you think of cyclohexane is think of the chair form. Just assume that it's always in the chair form. But it does undergo some twisting through other forms. And the boat form actually isn't the only quasi-stable energy minimum. There are several others. There's a twist boat, for instance, that's sort of in between the boat and the chair. The chair form is what we call the local minimum computation, the global minimum of most stable structure. The boat form is a local minimum. It's in a potential energy well, but it's not as stable as the global minimum, the chair. And remember, every time the ring flips from chair to chair, everything that was axial becomes equatorial, everything that was equatorial becomes axial, and that can change the energy profile because your bulky groups prefer to be equatorial. And conformation that has the maximum bulkiness in the equator of the ring is the best. Now, there's another thing here that's not obvious I have to point out, very important. Let me go back to the ball and stick. Okay, so you notice the way the axial positions alternate up, down, up, down, up, down as you go around the ring. The equatorial positions do also. So if you look at this equatorial hydrogen, notice how it's pointing up. Right here. The one next to it is pointing down. It's a more subtle up and down direction, but it's still there. When you're talking about stereoisomers and cyclic compounds, that would be what we call cis and trans. If you have these two chlorines, for instance, are on opposite sides of the ring. They're trans to each other. If they were on the same side of the ring, like these two, these are cis to each other. Trans and cis, C-I-S, refer to same side of the ring or opposite side of the ring when you're looking at two particular substituents. And they're locked in that position. If they're trans, they cannot escape that fate. Even if the ring flips, like these two chlorines are cis to each other. If this ring flips and these two chlorines go equatorial, they'll still be trans. They won't be as dramatically on opposite sides of the ring as before, but they will still be trans. So trans and cis never change. Axial and equatorial do as the ring flips, but trans and cis is permanent, cannot be overcome. And that's because of the restricted rotation of the ring. This flipping is only a minor rotation. If two groups are on the same side on the ring can't twist around the carbon-carbon bonds enough to make them trans. It can only twist a little bit. So again, cis is permanent and trans is permanent. Those are what we call geometric isomers. Yes. Yes, but not with this program. It doesn't do that. Well, if it flips, everything that's axial, well, I can make it that way. So if I take these chlorines and make them all hydrogens, and then go to the equatorial positions, come around here to see them again. Missing one right here. Okay, so this is a case where all of the fluorines are equatorial and all of the hydrogens are axial. If you look at the space filling, you can see that this is better. The chlorines are pretty much separated. They don't overlap at all, which is what they did when they were occupying these axial. The white spheres, the white eggs there, those are the axial hydrogens now. And the chlorines are spread out further in the equatorial position. In fact, let's see, you can minimize that. Yes. Right, the program is adjusting the bond lengths and bond angles and portions, driving it to a minimum energy. And the total energy is 7.6 for having all of the chlorines equatorial. Let's go back here and reverse this. Okay, so now all the chlorines are axial. See, the energy now, instead of being 7 kilocalories per mole, is 32 because of that crowding of the chlorines when they're in the axial position. It's the same molecule, but now all the chlorines are axial. So as the ring flips, this would be the higher energy chair form, and when it flips so that they're all equatorial, that would go down to 7 kilocalories per mole. So there's quite a substantial difference in energy, but of course you've got 6 chlorines on the ring. And I set this up so that the positioning of the chlorines allows them all to be equatorial or all axial at the same time. You can shift this. So if I take one of these chlorines and replace it with a hydrogen, and so now one of the chlorines is equatorial, that isn't as bad, but the others are. So if we calculate the energy, it should go down. You can see instead of 32, it's 26. So one chlorine moving from axial to equatorial dropped it about 6 to 7 kilocalories per mole. Just demonstrates that crowding problem. Now let's look at it like this. Okay, so this is the one I altered where one of the chlorines was not axial. 1, 2, 3, 4, 5 are axial. These two chlorines right here, are they cis or trans? Cis. Even though this one is equatorial and this one is axial, they're both pointing to the bottom side of the ring. So you have to watch that. Right next to one another, if they're cis, they'll both, one will be equatorial and the other axial. Right next to each other, if they're both axial or both equatorial, they have to be trans. There's a very complicated flip-flop relationship between cis and trans and equatorial and axial. And there are a number of problems in the book that say, for instance, is 1,3 cis 1,3-dichlorocyclohexane more or less stable than trans 1,3-dichlorocyclohexane? What you would have to do is be able to parse that into equatorial and axial, and being 1,3. So if they're cis and one's axial and the other's equatorial, is that cis or trans? And if they're both equatorial, is that cis or trans? It can get very complicated, but you need to be able to do that. You need to be able to navigate around. Cyclohexane, the six-membered ring, is the most important cyclic structure in organic chemistry and in nature. And this business of cis and trans and equatorial and axial is related, and there's a pattern in that relationship, but you have to own it. You have to work with, you can do it on pencil and paper or with a modeling program or with a set of molecular models, but you need to work that out in your head. There is no trick to it other than just understanding what's going on and getting a system for yourself so that you can figure that out. Now, quite often you see the rings drawn, not in the chair form, but just flat like this. The understanding is that it's in the chair form. The advantage of drawing it like this, and the view would be that it's not in the plane of the board, but it's perpendicular to the board. So you're looking at it like my hand, on edge. Not like this, but like this. That way you can indicate cis and trans very easily. So that's obviously trans 1,3-dichlorocyclohexane. You have to exaggerate the up and down, and that's what this kind of type of drawing does. The other one is cis 1,3-dichlorocyclohexane. They're both 1,3-dichlorocyclohexane. The one on the left, though, has a different three-dimensional, baked-in stereochemistry. If the stereochemistry is baked into the molecule, in other words, it cannot be changed, then you have stereoisomers, such as the cis and trans in the cyclic compounds. those are not interconvertible. They have different melting points, different boiling points. They have permanently different compounds, and that have to be respected that way. The stereo descriptor out in front of the name is what will distinguish them. So that's 1,3-dichlorocyclohexane. The one on the left is trans 1,3-dichlorocyclohexane. Put that right out in front of the name. Call that the stereo descriptor. And the other one, I'm sorry, the other one is trans. The one on the right is cis 1,3-dichlorocyclohexane. If the only difference between two compounds is a baked-in three-dimensional difference that's frozen, baked in, then they're stereoisomers. They're not structural isomers. They're stereoisomers. Anywhere, but obviously at a substituent. You start, good question about the numbering on the ring. You start where you have a substituent of interest, and then you go the short route to the next substituent. So 1,3-dichloro, not 1,5-dichloro. Don't go the long way, but the short way. And in other words, keep the numbering system as small as possible. This is 1,2-dichlorocyclohexane. That is a structural isomer of either one of the 1,3-dichlorocyclohexane. If two compounds have a fundamentally different bonding pattern, they're not stereoisomers, they're structural isomers. You only call two compounds stereoisomers if the only difference is a baked-in three-dimensional configuration. And there are actually three causes for that. One of the three is the subject of chapter 5. The other two are in chapter 4. A ring, which freezes the rotation, and a carbon-carbon double bond, which also freezes the rotation. You can't rotate around a carbon-carbon double bond, so that is permanently cis 1,2-dichloroethene. The trans is a different stereoisomer. Those cannot be interconverted. The one on the left is trans 1,2-dichloroethene. So restricted rotation causes two of the three types of stereoisomers. And it's the same thing whether it's a ring or a double bond. It's restricted rotation. Those collectively are called geometric isomers. Okay, good question. Stereo terminology here. Stereoisomers, that's the general term. These are compounds where the only difference is a permanent three-dimensional difference. Everything is still bonded in the same connectivity pattern. They're not structural isomers, they're 3D isomers.